Welcome to our mathematics lesson, of which we are continuing with algebra and numbers. And today, I want us to look at terminating decimals, recurring decimals, and rounding. Terminating, recurring, and rounding. Earlier on, we find that we are able to convert any fraction into a decimal. But today I want to say this: not all fractions, when you convert them, they will terminate. Those fractions which we've been handling, we've been able to find the exact value in decimal. For example, 1/2, when you convert it, it is 1 divided by 2, which will always give us 0.5. And it terminates. So those conversion, those fractions which gives us exact value of a decimal, we call them terminating decimals. However, can you try this and see what will happen? Convert 1/3 into decimal. Convert 1/3 into decimal. What do you notice? It was 1 divided by 3, which cannot go into 3, so we put a 0 point, and then we have 10 by 3 is 3, gives us 9. Remainder 1, 10 by 3, 3 into 3 is 9. Remainder 1, again 10 by 3 is 3. So you notice that the 3 is recurring. So when you convert a third into fraction, you'll have 0.333. It is endless. What is this? What's happening here? So we have got some fractions which we cannot convert and get the values directly. It will not terminate. It will keep on repeating itself in a certain pattern. So that is when we talk about what we call recurring or repeating decimals. So what should we know about these decimals that terminate and decimals that recur? We find that a terminating decimal has got an exact number of decimal places. A terminating decimal has got an exact number of decimal places when you try to convert. What we are trying to say is that a terminating decimal has a finite number of decimal places, that is, it terminates. Take, for example, 5/8. When you try to convert 5/8 using the method that we know, you'll find that it is 0.625. And you'll find that nothing will go on. It will end at that particular point. You can use a calculator to get it that way, or alternatively, you'll have to do it the longer way. So this is 0 point. We have 50 into 8 gives us 6. That is 48. Remainder 2. 20 into 8 goes 2, which is 16. Remainder 4. 40 into 8 gives us 5. So you find that 5 over 8 is equal to 0.625. This is a terminating decimal. It has got an exact number of decimal places, that is 3. It terminates. A recurring decimal, or what we are calling repeating decimal, has an infinite number of decimal places with a finite sequence of digits that are repeated indefinitely. So we are going to have the number of decimal places repeating endless, but there will be a certain pattern of certain digits repeating themselves. That is what we call a recurring decimal. As we saw earlier, we were trying to convert 1 over 3, and we found that it is 0.333 and so on. 1 over 3, when we converted, we got... What pattern do you study here? The pattern that you study is that 3 is repeating itself so many times. Therefore, 1 over 3, when you convert it, gives us a recurring or a repeating decimal. I want to say that all the terminating decimals and all the recurring decimals can be converted into a fraction. All numbers are expressed as fractions. That is something we should note. Be they terminating decimals or recurring decimals or any other number, they can be converted into decimals, into fractions. So if that is the case, we can convert any number into decimals, and we can also convert all decimals into fractions. Now, when you write A over B, where A and B so we are saying that all numbers can be written as fractions, that is in the form of A over B, where A and B are both integers and B is not equal to 0. If that is the case, then we call all these numbers rational numbers. The numbers are rational. Now, in our conversion, we have seen that repeating or recurring decimal has got a pattern that is endless. So what or how should we represent this while we are converting fractions into decimals? So for us to be able to finish the decimal, we need to show that it is a decimal, but it is what? It is recurring. A convention is to use dots placed above the digits to show the start and finish of cycle of digits, to show the start and finish of repeating cycle of digits. Now, what are we trying to say here? We don't need to write endless decimals in our book. But there is a way, and that's why we are saying we use a convention to simply show that we have 0.3333. What digit is recurring? That digit that is recurring is where we place the dot. And the digit that also terminates, keeps on where it terminates, is where we place it. So, but for this case, we shall say this is 0.3, and this 3 is what starts the recurring, and the same 3 is what ends the recurring digit. So we shall write 0.3 with a dot above. If we have, for example, the pattern of about 3 digits keeps on recurring in a certain pattern, then we, for example, class, look at this pattern. What do you notice? What digits are showing some signs of certain sequence of repeating themselves? When you look here, you'll notice that we have 0.3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2. Definitely the next digit will be 3 and then 4, 1, 2. So instead of writing all these, then we simply say this one can be written as just 0.3412. The start of the recurring, we are talking of the start of the recurring digit here is 3. And the end of the recurring digit, when you look at this, is what? 2, before we start again repeating. So we shall place a dot above. We shall place a dot above those digits which are recurring. That is 3 and 2. So you don't need to add all the others, just this. Supposing the digits that were recurring comes after some decimal places. Zero 0.26577777. So 7 is the one recurring. So the 2, 6, and 5, we shall not put anything above it. So it will be 0.265, and then 1 that is recurring, we place it with a dot above it. That is how we can simply write briefly, precisely a recurring decimal. We also have another way. If we don't want to use dots above them. Another way, if we don't want to use a dot, another convention is to use a bar. For example, if 0.555 is recurring, then we shall just say 0.5 and put a bar above the recurring digits. If we have got a pattern of certain number recurring, for example, 0.3412412412412, 3 is not recurring, but 412412412 is recurring. Instead of having 0.3412 with 2 dots there to show the start and the finish, we can also use a bar, 0.3 and 412. The recurring digits we place a bar above them. We shall have shown that these digits are recurring. Now, you realize that this situation that recurring decimals puts us in requires us now to have a knowledge of what we call rounding, so that we can choose to have exact number of decimal places. So rounding is also very important. What do we understand by rounding decimals? To round decimal is simply to define the number of decimal places we wish to have. And then we shall now say, instead of writing all this, can you round this to 2 decimal places? So you'll be concerned about only 2 decimal places. So rounding decimals involves approximating a decimal number to fewer decimal places. Now, if we are approximating decimal number to fewer decimal places, for example, we want to go for 2 decimal places, there are some issues we should put in mind. One is the critical digit, and 2 is what we call the rounding digit. Taking, for example, here, we want to round this decimal number to 2 decimal places. So we shall go to where we have the decimal point, and we count 1, 2. That second digit is what we call the rounding digit. So for this case, 4 is our rounding digit. The digit that comes immediately after the rounding digit, we call it critical digit. That is, this case, it is that 1, we call it critical digit. So, what should we have in mind about rounding digit and critical digit? For us to round decimals, we need to look at these two, and the following must apply. If the critical digit is less than 5, then rounding digit is not changed. It's not changed. For example, if we are to round this to 2 decimal points or places, then we shall look at 1, 2. This is the 4 is the rounding digit, and 5, the 1 is the critical digit. So we are saying here, if the critical digit is less than 5, then rounding digit is not changed. So here, critical digit is 1. 1 is less than what? Than 5. Therefore, we shall have 0.34 correct to 2 decimal places as our answer, because it will not change because the critical digit was less than 5. If the critical digit is greater than 5, rounding digit is increased by 1. So what are we trying to say here? Look at the following. Round off 2.3365 to the nearest or correct to 2 decimal places. Correct to 2 decimal places. Here, our rounding digit is 3. Our critical digit is 6. Class, is 6 greater than 5 or less than 5? You'll notice that 6 is greater than 5. If 6 is greater than 5, what happens to the rounding digits? It is increased by 1. So when we write this, we shall write 2.3, and then the rounding digit is increased by what? By 1 from 3 to 4. And that will be our answer correct to 2 decimal places. So we are saying here that to round numbers, we need to know the behavior of the critical digit, which varies. If it's from actually like 0 to up to 4 point something. The moment you start reaching 5, then you have to increase the rounding digit. When the critical digit remains below 5, the rounding digit remains as it is. That is what we need to observe when we are looking at rounding. So let us look at exercises and see how well do we apply these in mathematics problems. Convert the following fractions into decimals: A quarter or 1/4 and B 7/8. I want us to start with the first one. 1/4. This one can be converted straight. We can have it as 1 into 4, which is 0 point. We have 10. 10 into 4 is 2, giving us 8. With a 2, bring a 0. 20 into 4 is 5. And this one has terminated. So we say that 1/4 is equal to 0.25. That is a terminating fraction. That is this fraction gives us a terminating decimal. For the second one, 7/8. So 7 into 8 we cannot. So we put a 0, bring a 0 here. Then we have 70 into 8, and 70 into 8 will give us 8 because of 64. We remain with 6. When you bring the 60 into 8, this one will give us 7 because of 56. And finally, 40 into 8 will give us 5 because of 40, and this terminates. Therefore, 7/8 is equals to 0.875. It is a terminating decimal. So that is what we get when we convert a quarter, and also when we convert 7/8. For 7/8, it is 0.875. It is a terminating decimal. Express the following fractions as recurring decimals. Remember, we are going to use convention. You express the following fractions as recurring decimals. So the first one is 2/3. If you use your calculator, you'll be able to find it is the same as 0.6, and 6 is recurring. We can do it manually and see what it gives us. So this one will give us 20 into 3 is 6 because of 18. Again, 20 into 3 gives us 6 because of 18. Again, 20 into 6 into 3 gives us 6. So you notice that we are having a 0.6 recurring. So by convention, we can say this is the same as 0.6 or 0.6 with a bar. You can use a dot, or you can use a bar to show that the terminating and the start and end of the recurring digit is 6 for this particular case. So that is when you convert 2/3 into a recurring decimal. For the second part, we have a whole number and a fraction. As we have seen in our previous classes, a whole number is not affected because a fraction and a decimal simply forms part of a whole. So when we have a whole number and a decimal, then the same will form a whole number and a fraction. So where we have a whole number, it will remain. Our interest will go into converting the decimal part. So for that case, 3 and 5/7 is simply the same as 3 plus what the fraction we want to convert, which is 5/7. So using your calculator, if you divide 5/7, you'll find that when you use your calculator, this is what you'll get. 5/7 will be 0.714285, and so on. So by convention, we can now say we can rewrite this as simply 3 plus 0. Now, what is the starting digit that is giving us the pattern to recur? In this case, you find it is 7, so we shall have a dot above 7. And then the last digit to recur before we start recurring is 5, so you'll have a 5 there. Above 5, we shall have a dot. So when you add this, you find it is 3.714285, but above 7 and above 8, we have dots to show that this decimal is recurring. Or with a bar starting from the first digit that starts to recur to the last digit. So you can simply convert 3 and 5/7 into recurring decimal, and this is what we get. So, having said this, for the recurring decimals, we cannot occupy the whole page to represent a decimal, but we should be able to round the decimal into the required definite number of decimal places. Round the following to specify number of decimal places. The first one, 15.35729, correct to 3 decimal places. And 4.8619502, correct to 4 decimal places, correct to 4 decimal places. Now, this is where we now look at the following, the 2 digits we call the critical digit and the rounding digit. We should be able to identify those 2 digits. So from the first one, I want us to first identify the rounding digit and the critical digit. We want 3 decimal places, so this is 1, 2, 3. That is the point at which we are looking at. When you look at that particular part here, then you find that 7 is our rounding digit and 2 is our critical digit. We said earlier on that if the critical digit is less than 5, then the rounding digit is not changed. So for this case, 2 is less than 5. Therefore, we are not going to change the rounding digit. We only go in for the number of decimal places. So when you rewrite this to correct to 3 decimal places, it will be 15.357. And this is correct to 3 decimal places. For the second part, we are to round off correct to 4 decimal places. If we have to round to correct to 4 decimal places, we first identify the critical digit and the rounding digit. So we count number of decimal places, 1, 2, 3, 4. From the 4th, at that point there, we find that 9 that we have here is our rounding digit, and 5 is our critical digit. So if that is the case, then we look at the critical digit. Is it greater than 5 or less than 5? Remember, critical digit, if it is 5 and above, where 5 is inclusive, then the rounding digit will be increased by 1. For this case, it is showing us that critical digit is 5 and above. Therefore, rounding digit will be increased by 1. So we shall have 9 increased by 1, and 9 plus 1 is 10. So which will give us a 0. So we are talking of 4.8619. We are increasing by 1. So this one will give us 0. Because 9 plus 1 is 10. Carry 1. Then 1 into add 1 gives us 2. This is 6. This is 8. Point and then 4. So we find that correct to 4 decimal places, when we round the decimal above, we shall have 4.8620. Remember, the rounding digit was increased by 1, and it was 9. We cannot write 10 as a digit, so we write 0, we carry 1 to the next column, and 1 becomes 2, and that's why we have what we have there. So we have seen how to convert fractions into decimals, and for those recurring decimals, we are simply able to write by convention and show that these are the recurring digits, so we don't need to struggle about them. And finally, now we want to see, can we just go straight and round and convert a fraction directly into a decimal and round to specified number of decimals? Write 3/7 as a decimal, correct to 2 decimal places. Correct to 2 decimal places. So using a calculator or a long method, we can always be able to convert this. So 3 cannot, so we have 0, and bring in a 0 here. Then we have a decimal point directly above the dividend. So 30 into 4 will give us 30 into 7 will give us 4, which is 28. 20 into 7 will give us 2. Now we have 60 into 4, into 7, sorry, will give us 8. Now you realize that at this point, our interest was correct to 2 decimal places. We do not need to go on and on and on. We have 2 decimal places and we have the 3rd decimal place, which means we are able to have our rounding digit and our critical digit. So let us get back to that and see. So what we have is 0.428, and from 4 to 8, we have our rounding digit as 2 and our critical digit as 8. 8 is greater than 5, therefore the rounding digit is increased by 1. So this one becomes 0.43. It becomes 0.43, correct to 2 decimal places. So there was no need to go on, and yet you've reached where you can be able to find the critical digit and the rounding digit. Now, we should by now be able to find what fractions do terminate and which fractions do not terminate. We have seen how to convert fractions into terminating decimals, fractions into recurring decimals. But now I want us to look at one part of a decimal whereby we have a recurring decimal and we need to convert it into a fraction. Not all fractions, decimals can be easily converted. The simple decimals are straightforward, converted. For example, if you have a fraction like 0.5, to convert 0.5 into a fraction, because we have one decimal place, this is the same as simply saying over what? 10 down here. Or I would say 0.5 over 1 multiplied by 10 here, multiplied by 10 here. This is 5 over 10, which is equals to, by 5 is 1, by 5 is 2. So we are saying that when you have 0.5, when you convert it, you'll get a half. We can easily convert that. If you have 0.3, this is again the same as over 1 multiplied by 10, because it is one decimal place. To multiply by 10, this becomes 3 over 10. The situation arises now. What about if this decimal was recurring? Will it give us the same answer? So I want to bring a difference between 0.5 and 0.5 recurring. That is where the difference is. We know that 0.5 is a half. But 0.5 recurring, is it equal to a half? So because this is the same as 0.55555 recurring. So it's necessary that we look at a method of how we shall resolve this. So we start by saying now, let R be what we have 0.555 and so on. Then if we multiply R by 10, the way we were just doing, then it will mean multiply by R by 10, it will have 10R will be the same as what? You'll find that it will be the same as 5.555 recurring. So if that is the case, now consider that, just make sure you have the same number of decimal places. And then now we have got R is 0.5555 and so on, and we have 10R as 5.555 recurring. So when you take 10R minus R, the other side you should be having 5.555 minus 0.555. I choose to use 3 decimal places up to 3 decimal places. I'm not rounding off, it is just truncated like that. So 10R minus R is 9R. And the other side, you'll realize that the decimal part will just go. We shall remain with 5 minus 0, which is 5. So as we saw earlier on, to make R our subject, we shall divide both sides by what? By 9 to get R, and divide this side by 9, you'll get 5 over 9. So we are saying that when you convert 0.5 recurring into a fraction, then we shall have our fraction being 5 over 9. If you can try to convert it backwards, you'll realize that 5 over 9 is the same as 0.5 recurring. It has always been good to check our answer. But I want you to note the difference. This is 0.5. We just got straight a half, as you saw earlier. This is 0.5 recurring, but what we are getting is a different value, which I'm calling 5/9. Can we see if it's true by converting 5/9 and see what shall we get? To convert 5/9 into a decimal, it is 5 divided by 9. 5 divided by 9. This is 0. And you find 50 into 9 is 5. Because of 45. We have 5 balance. 50 into 9 is 5. Because of 45. We have 5 balance. 50 into 9. So you are getting 5 recurring. Therefore, this is 0.5 recurring. So I was trying to say that to convert recurring decimals is not the same way we convert terminating decimals. They are different. And when you convert terminating decimal, it's straightforward. But for recurring decimal, we need to assign values and see how we work on it. So that is if we have a decimal. Supposing we have a whole number and a decimal part. When you look at this, you'll always know that because we have a dot above 6, it is telling us 6 is recurring. On this other side, what we have is what? What we have on this other side is a whole number, so there's nothing much about it, but we want to convert it into a fraction. So what will happen here? So as we saw earlier on, that we start by assigning a value. So by saying, we choose to say, let, now we have 1 point. This, we don't separate this time that we have all numbers, so put a whole number aside, although it's one of the method. You can choose to say, because a fraction will still have a whole number, let us keep aside the 1, and then we proceed. But also, we can simply go straight and say, let R be equal to 1.666 is recurring. 10R will be 16.6 recurring. When converting recurring decimals, I've said you will assign this pronumeral to what you have, and you realize that this is 1.666. So I'm expecting to have, and when I multiply by 10, it is 10R this side on the left-hand side. The right-hand side will become 16.66 recurring. Then we subtract, take 10R minus R should be equal to the right-hand side, which is 16.66 minus 1.66. In subtracting decimals, we said earlier on, we must arrange them, each one in its place value. And if we do that here, it is 16.66, and we have 1.66. So this one will give us 0, 0, so we have 15. So, which means 10R minus R is 9R, is equals to 16.66 minus 1.66 is simply 15. So then we divide both sides by 9. Divide both sides by 9. We'll find that R is equals to 15 over 9. 15 over 9. That is what we have. Can we check our answer and be sure? Because what we had was 1.6 recurring. If you are trying this into mixed as a mixed numeral, it will be 1, and then what remains is 6 over what? 6 over 9, and 6 over 9, when you simplify, it is 2 over 3. So if we are to check our answer backwards, from what we just have, you either choose to say 15 divided by 9, or you say, because you have 1 and 2 over 3, this is 1 point. Now 2 over 3, we can look at 2 over 3 like that. So for this one, it is 1 point. We say the decimal point should be directly above. So 1 cannot divide into 9, so 15 goes 1, so 1 is 9. What remains is 6. So we bring this 0 down. And when we take 60 divided by 9 is 6. Because of 54. Again, 60 is 6. Because of 54, again 6 is, and so on. So you realize you're having 1.6666 recurring, which is 1.6 recurring. So we are trying to say that when you convert a recurring decimal into a fraction, you should also be able to convert the decimal itself into recurring. The changes that has come here is that a terminating decimal, the way it is converted, is not the same way on how we convert what I'm calling the recurring decimal. So, given a list of fractions, are you able to identify which ones are going to terminate and which ones are not going to terminate? So check on the following and explain whether it's going to terminate or not. But also, when you use your calculator, it is easier as long as you are able to study the pattern. Okay, looking at the first one, we have 1 over 8. When you divide 1 over 8, you find it gives us 0.125. So, is it terminating or it's not? It is terminating. So we are saying this is, let t be for terminating fractions, decimal. So an eighth gives us a terminating decimal. 1 over 12. When you look at 1 over 12, whichever method you'll use to work out, so 1 over 12 will give us 8, and then it is 0.8, and then 3, 3, 3. So 3 is recurring, so you can say that this is a recurring decimal. 1 over 14. So remember, we are only using the pattern about recurring. You look at the digits, the behavior, and then you state whether it is going to recur or it's not going to recur. Now, when you look at 1 over 14, this is a very interesting one. 1 over 14, when you convert into a decimal, you are going to get 0.071428. Then we have 714. What do you notice here? There is something happening. We have 0.0714285, and I expect 285, and so on. So this C, which is 1 over 14, forms what we call a recurring decimal. How about 1 over 15? 1 over 15. 1 over 15 will give us 0.0666 recurring. So you can say that this is a terminating. This is a terminating, not a terminating, but a recurring decimal. So at your own time, look at 1 over 20 and look at 1 over 60. Study the pattern of the behavior of the decimal places. You'll always be able to tell if it's a terminating decimal or if it is a recurring decimal. That is it for now. Thank you.